Today we will introduce the subject of machine learning operations, or in short MLOps. So what is MLOps? MLOps is a combination of machine learning and DevOps. Machine learning is the practice of training models so that a machine can learn and solve problems on their own. And DevOps is the integration and automation of software development and IT operations. So when you have a new software program, you can release it automatically and deploy it. When you translate this to machine learning, you get the automated creation, deployment, and maintenance of machine learning models. The comic on the right explains this. Without DevOps, one could say that, oh, this code works on my machine, but it doesn't work on another. So with DevOps, you can avoid this. And the same on the right side, oh, this model works well for my training data, but it does not work well for on another training set. This can also be avoided with MLOps. So why would someone invest time and money into MLOps? This is because MLOps guarantees more accurate, reliable, adaptable, and scalable machine learning models. This is because there is almost no human input, so there's, for example, less chance for human error. And also it reduces time and cost of deploying and maintaining the models massively, because now when you have a new model, you don't have to train it yourself, you don't have to clean it yourself, but this can all be done by the MLOps pipeline. So this reduces time and cost massively.
MLOps consists of four key components. The first key component is data engineering. In this component, data gets collected and processed to be further used in the next component, which is model development. In this component, a model gets trained and developed for this data, and then needs to be deployed in the next component, which is deployment and monitoring. Obviously, it also needs to be monitored during its deployment. And lastly, the last key component is continuous training, which means continuously improving the model and adapting it to changing data.
So the second part of the machine learning workflow is data engineering. And in data engineering, we typically start off by combining data from different sources like spreadsheets, databases, and so on. We then explore them using frameworks like Apache Spark or Jupyter Notebooks. And from the analysis and exploration, we try to improve the quality of the data. This can be by imputing missing labels in the data or detecting outliers, removing them, or we can also augment the data. But where does MLOps come into play here? Well, if we want to automate the process and if we want to make it reproducible, we should also version our data sets. If we keep making improvements, we should track these improvements, just like we do with software through tools like Git. And at the same time, closely related to this, we should have data pipelines which can immediately say the quality metrics for our data and test in a similar fashion. The next part in the machine learning workflow is the model development. In this stage, we create a model that will do the predictions. And this starts off by feature engineering, where we take our cleaned input data and extract useful features from them, which can be used for predictions. And then we create our model. We combine different algorithms, or we set different parameters differently to obtain many different models, to obtain many different experiments. And these experiments are evaluated in terms of offline metrics like the precision, recall, accuracy, F1 score, and many others. But where does MLOps come into the picture here? Well, at first we may want to do this all automatically. We would like to automate the entire 3 steps described here. This is what AutoML tries to do, and it uses approaches like deep learning to just make the developer give their input data and spit out a good model for the developer. But the other approach is through using continuous integration techniques and experiment tracking. Continuous integration and experiment tracking in machine learning starts off just like in software engineering by defining pipelines of how we get to our models, how we get to our software. And these stages, like shown in this graph here, can consist of extracting certain features of the data set, training models, but also combining different trained models into an ensemble. And the outputs of these pipelines are registered through tools like MLflow and TensorBoard to track our different models. And we keep all these older models to be able to keep comparing them to older models, like an A/B testing. We always compare our model with an older one to keep track of the improvements that we've made and make sure that we are continuously improving our models. The last part in our workflow is the model deployment, and it does start off with the deployment itself, where we pack our model into an API, like a RESTful API, and deploy it, serve it onto a runtime like Docker or Kubernetes. But it doesn't stop there. After we've deployed the model, we also keep monitoring it to look at scores that we previously measured offline, like the accuracy, the F1 score, and so on. But we also keep track of how many resources we are using to monitor sustainability, and also if our application is being used legally, if it's being used as it is intended. And MLOps works on both aspects here. We have the continuous delivery that works on model packaging and serving, and we have continuous training that is triggered by our monitoring.
In MLOps, new pipeline implementations are continuously delivered to the target environment that in turn delivers prediction services of the newly trained model. The delivery process can be separated in first serializing the ML model and then serving it. In the past, the serialization was done using pickle files or other vendor-specific formats, but MLOps promotes more language-agnostic approaches, such as amalgamation and using file formats such as OnNX or PMML. MLOps also allows us to automatically serve the serialized models using tools such as Kubeflow or Seldon Core.
Continuous training, on the other hand, relates to the model being effectively in deployment, being used, and tracking how it is doing. Like there can be many changes, like changes in the data and changes in the concept how the model is being used. Like the input data that's coming in could become different over time, but also other things could become different that affect the model. Like in fraud detection, we used to be able to detect it if we could see large cash deposits, while nowadays the emergence of bitcoins changes this, and cash is less used in some fraud cases. So we need to keep track of how our model is performing. And when our model exceeds the given threshold of performing worse, then we should retrain the model. This is the essence of continuous training. We keep retraining the model when it is doing worse than a certain threshold. And this is something very unique for machine learning, because in software development we would not be able to do this, as there would be manual label required to create new versions of the software. So this is somewhere where machine learning gives us an additional way to add automation to the entire process.
Because MLOps is quite a new practice, there are still some shortcomings and challenges. The first challenge is automatic data labeling, because it is easy to collect data, but not so easy to have this data labeled. There are two ways to handle this. Either you find a way to automatically label this data, or you find a way to handle this unlabeled data. For example, just use it to improve your model. The second challenge is explainability, because the whole flow can be automated and a machine learning model can just be can be made completely automatic. It becomes more of a black box than before. During this presentation, we went over a lot of tools. These tools were mainly for individual components, but there also exist tools who completely automate the whole flow. I hope you learned something today, and thank you for watching.